Imagine this scene. Detectives stand over a body in a dimly lit alley. The forensic pathologist kneels, touches the neck, stares thoughtfully at nothing for 2 seconds, and announces, "Time of death, 10:17 p.m." Everyone nods like that's perfectly normal. That's what television taught us to expect. But in real forensic pathology, that level of precision is almost pure fiction. In this video, we're pulling apart the biggest myths around one of the most misunderstood ideas in death investigation: time of death. We'll look at what pathologists can really know, what the evidence actually shows, and why even the best experts often speak in broad windows, not exact times. If you've ever watched a crime show and thought, can they really do that? This episode is for you. Let's start by separating dramatic storytelling from the messy, uncertain reality of human biology and decomposition. Before we dive into rigor mortis, body temperature curves, and creepy crawly insects, let's set the stage. Forensic pathologists are medical doctors who specialize in figuring out how, and sometimes when, someone died. But here's the twist. Real life almost never gives them the neat timestamps you see on TV. Instead, they work with ranges, probabilities, and a lot of uncertainty. In this video, we'll break down the classic tools: algor mortis, rigor mortis, livor mortis, stomach contents, entomology, and explain what each can and cannot tell you about time of death. We'll also touch on why courts have become more skeptical of precise time of death claims. If you're interested in true crime, medicine, or just like pulling back the curtain on TV myths, stick with me until the end. And if you enjoy evidence-based breakdowns like this, consider subscribing and hitting the notification bell so you don't miss future deep dives. Let's start with the core misconception that there is a single knowable time of death. Biologically, death is a process, not a light switch. Cells die at different rates. Organs shut down on slightly different timelines. Even after the heart stops, certain tissues remain metabolically active for a while. When forensic pathologists talk about time of death, they're really estimating a post-mortem interval, the time between death and when the body was discovered or examined. And that interval is almost always expressed as a range, between 8 and 12 hours, or likely more than 24 hours, but less than 48. Precise times down to the minute, or even the exact hour, are usually guesses dressed up as certainty. The reality is influenced by clothing, body size, environment, disease, medications, and countless tiny variables. So the first myth, that time of death is a single sharp number. In practice, it's a probability zone, not a timestamp. TV often shows the pathologist pinching the skin, maybe touching the wrist, and then confidently calling a time within minutes. In reality, even under ideal conditions, most textbooks admit that after the first few hours, error margins expand quickly. Early after death, some things can be roughly timed. The absence of a pulse, lack of breathing, and certain eye changes might suggest someone died very recently, but usually you already know that from the situation. As the hours pass, biological signs become less precise. Outdoor environments, extreme temperatures, immersion in water, or heavy clothing demolish neat schedules. Even in controlled lab settings, humans don't behave like identical thermometers. One classic review famously concluded that most time of death estimates beyond the first few hours are, at best, educated guesses. So when TV characters declare 10:17 p.m. plus or minus 10 minutes, you're watching fiction, not forensic medicine. One of the oldest tools for estimating time of death is body temperature, algor mortis. The idea seems simple. Bodies cool at a predictable rate, so just measure and calculate. In practice, it's far from straightforward. The classic formula, about 1.5 degrees Fahrenheit per hour, assumes a naked body in a temperate room with no wind, moisture, or unusual illness. Reality rarely cooperates. Clothing acts like insulation. Obesity slows cooling. A thin person cools faster. A body on cold tile behaves differently than one on carpet or in a warm car. Fever, alcohol, or certain drugs change starting temperature. Even airflow, humidity, and whether the person was lying on metal or wood matter. Forensic guidelines now treat temperature-based estimates as one data point among many, not a standalone clock. When you hear temperature suggests death 6 to 10 hours ago, that's already a broad, cautious range, not a mathematically precise answer. Rigor mortis, the stiffening of muscles after death, is another favorite TV trope. You've seen it. The detective lifts an arm, feels resistance, and the pathologist instantly concludes he's been dead 6 hours. Scientific reality is messier. Rigor appears as ATP, the cell's energy currency, is depleted after death. It usually begins within 2 to 4 hours, becomes fully developed around 8 to 12 hours, and fades after 24-36 hours. But those numbers are averages, not rules. Temperature, prior exertion, illness, and even how muscular someone was can speed up or slow down rigor. A person who died after struggling intensely may develop rigor faster. Someone in a cold environment may develop it more slowly, but it could last longer. Because of all this variability, modern forensic practice uses rigor as a rough indicator, compatible with death within the last day, not as a precise stopwatch, despite what crime dramas suggest. Livor mortis, the purplish discoloration where blood settles in the lowest parts of the body, is another classic sign. You'll sometimes hear, lividity is fixed, so he died 8 to 12 hours ago. The truth, lividity offers clues, but not finely tuned timing. After death, the heart stops pumping and blood passively settles under gravity, creating reddish-purple patches. This begins within roughly 30 minutes to a few hours and becomes more obvious over the next several. Over time, as red cells leak and hemoglobin stains the tissues, the pattern becomes fixed, meaning it doesn't blanch easily when pressed or when the body is moved. But the rate depends heavily on temperature, cause of death, and even skin color and body position. Livor mortis is often more valuable for telling whether a body has been moved after death than for clocking the exact interval. Fixed lividity can support a broad time frame, but it cannot credibly narrow death to a specific hour. What about stomach contents? TV writers love this one. He ate steak and mashed potatoes at 7 p.m., so he must have died around 9. The digestive system, however, doesn't own a clock. Gastric emptying, how quickly food leaves the stomach, varies massively from person to person and meal to meal. Fatty or heavy meals slow things. Liquids pass faster. Stress, alcohol, medications like opioids, diabetes, and many other conditions can dramatically change digestion speed. Even posture and physical activity make a difference. Studies trying to correlate stomach contents with time since last meal find enormous ranges, often several hours wide for the same type of food. Because of this, responsible forensic pathologists are extremely cautious. At best, stomach contents might loosely support a rough narrative if other evidence points the same way. Alone, they're a very weak basis for narrow time of death estimates, despite how confidently TV pathologists lean on someone's last sandwich. When bodies are found days or weeks after death, investigators often turn to entomology, using insects as biological clocks. Blowflies can arrive within minutes to hours of death, laying eggs that become maggots, then pupae, then adult flies in a fairly predictable sequence. By identifying species and developmental stage, forensic entomologists can estimate a minimum time since death. But again, conditions matter enormously: temperature, humidity, whether the body was wrapped or buried, indoor versus outdoor, urban versus rural, presence of drugs or toxins. Flies can't colonize a body that's sealed or deeply buried, so the entomological clock might start days late. Entomology is powerful for broad intervals, at least 3 days, likely more than a week, especially in advanced decomposition. Still, it's not a magic answer box. It's an informed estimate with error margins that grow when weather data or site conditions are uncertain, far from the instant lab analysis you see on screen. As decomposition progresses, the body itself becomes the main clock, but it's a very imprecise one. Textbooks describe stages: fresh, bloat, active decay, advanced decay, skeletonization. Each stage tends to correspond to certain time ranges under typical conditions. But what's typical? A body left on the surface in summer heat decomposes incredibly fast, sometimes skeletonizing in weeks. The same body in winter in shade or partially buried may decompose far more slowly. Clothing, insects, scavenging animals, soil chemistry, and even altitude can accelerate or delay each stage. That's why forensic anthropologists and pathologists often talk in broad terms: several days, a number of weeks, or likely months, rather than claiming this person died exactly 23 days ago. Decomposition stages help narrow vast ranges, but they're not precision tools. Whenever you hear a perfectly timed date attached to a highly decomposed body in fiction, remember how chaotic decay really is. On TV, the pathologist often announces a time of death that perfectly confirms or destroys a suspect's alibi. In real courts, things are more cautious. Over the past few decades, judges and attorneys have become increasingly skeptical of highly precise time-of-death testimony, especially in older cases where estimates were treated almost like hard science. Modern forensic references emphasize broad ranges and clear statements of uncertainty. A responsible expert might say, "Based on body temperature, rigor, and lividity, I estimate death occurred between 10 p.m. and 4 a.m., with greatest probability in the middle of that range." They'll also explain the assumptions: ambient temperature, clothing, body mass, and so on. Cross-examination often focuses on those assumptions, showing how small changes could shift the estimate by hours. The legal system is slowly learning that time of death isn't a single answer, but a sliding window built from imperfect pieces of biological evidence. So what can forensic pathologists do well with time? In the very early post-mortem period, roughly the first few hours, they can often distinguish just died from several hours dead using warm or cool skin, absence of vital signs, early eye changes, and initial lividity. Over the first day, patterns of rigor, livor, and temperature, considered together, can often narrow things to a broad window, maybe spanning several hours. In longer intervals, days to weeks, decomposition features and insect activity provide minimum times and rough categories, especially when combined with weather records. Importantly, these estimates get stronger when they align with independent evidence: phone records, surveillance footage, last known alive sightings, and digital data like step counts or device usage. Pathology is one piece of a larger puzzle. It rarely stands alone as the definitive answer, but when integrated with investigative work, it can strongly support or challenge timelines without pretending to be exact. Some of the biggest real-world time-of-death errors come from overconfidence in any single sign. For example, relying heavily on body temperature without accurate ambient readings, or trusting stomach contents despite unknown medical conditions. Another issue: outdated rules of thumb from older textbooks that treated cooling or rigor schedules as nearly universal. Today, forensic training emphasizes variability and error margins. Many high-profile wrongful conviction cases have involved shaky time-of-death testimony later challenged by newer science. That doesn't mean the entire field is unreliable. It means we now better understand the limitations. Modern pathologists are far more likely to say, "Here's what the findings are consistent with," rather than, "He died at 9:32 p.m." The myth isn't that time-of-death estimation exists. It does. The myth is that it's exact, simple, and always decisive. In reality, it's just one careful, uncertain voice among many in a criminal investigation. Let's pull together the key points so you can mentally fact-check the next crime show you watch. First, death is a process, and time of death is really an estimated interval, not a precise moment. Second, no single sign, temperature, rigor, liver, stomach contents, insects, or decomposition can give a perfectly accurate time on its own. Each is influenced by countless variables like temperature, clothing, body size, illness, and environment. Third, the further you get from the moment of death, the wider the error bars grow. Hours may become half-days, days may become weeks. Fourth, modern forensic practice and courts are increasingly cautious, emphasizing ranges and uncertainty rather than dramatic declarations. Finally, the strongest timelines come from combining pathology with digital evidence, witness accounts, and scene findings. If you remember that real forensic science is about probabilities, not certainties, you'll already understand more than most TV scriptwriters. If this deep dive into time of death myths changed how you think about forensic science, don't let it stop here. The next time a show confidently proclaims an exact time of death from a quick glance, you'll know what's missing: temperature records, environmental context, decomposition details, and a frank admission of uncertainty. If you want more long-form breakdowns that separate real forensic methods from TV fantasy, hit subscribe and tap the notification bell so you're here for future episodes. It genuinely helps this kind of evidence-based content reach more curious minds. Let me know in the comments which other forensic myths you'd like unpacked: bite mark analysis, bloodstain patterns, lie detectors, anything you've always wondered about. And if you found this useful, consider sharing it with a friend who's obsessed with crime dramas. Thanks for watching all the way through. I'll see you in the next investigation.